Chem 106, Chapter 17, Metal Ions. In this chapter, we're going to focus on the transition metals and the compounds that they make. So with transition metal complexes, when we say metal complex, what we mean is we have a metal ion, which can have a zero oxidation state. It doesn't have to be charged. It can be in its elemental form, we say. So it doesn't matter whether it has an ionic charge or not. We can still use it to make compounds with. And so a metal, which either can be charged or zero charged, bonded to a number of molecules, because again, using Lewis acid base theory, we can actually use molecules like water or ammonia or anything, or ions, so long as they have a pair of electrons on them that we can bond into d orbitals on the metal, regardless of whether the metal has a charge or not, as long as there are available d orbitals to bond into, then we have what's called a metal complex. If the complex has a net electrical charge, it's called a complex ion. If it has no overall charge, then it's just called a complex. Sorry. Compounds that contain complexes are known as coordination compounds, and the reason for that is that the pairs of electrons off of these, whether molecule or ion, that are bonded into the metal, those electrons form what are called coordinate covalent bonds. So we call these coordination compounds. Most coordination compounds are metal compounds formed by Lewis acid-based interactions involving transition metal ions. But again, it could be a metal in its elemental form as well. Alright, so then the molecules or ions surrounding the metal ion are called ligands. Some people will say ligand, but really it's ligand, as most of us say. But you will hear some people refer to them as ligand. Either way, ligand, ligand, it's just a word. All right, now the ligands act as Lewis bases because they have one or more pairs of electrons that they are going to donate into the empty d orbitals on the metal. So an electron pair donor is called a Lewis base. The metal then is going to be the electron pair acceptor, and so that's a Lewis acid. Lewis base is an electron pair donor. A Lewis acid is an electron pair acceptor. In coordination chemistry, then, the metal ions exhibit a primary and secondary valence. The primary valence is the oxidation state of the metal itself. The secondary valence is the number of atoms directly bonded to the metal ion, which is called the coordination number. So the metals in a complex are going to have an oxidation number, which is called the primary valence, and they're going to have a coordination number. How many? And it shouldn't say the number of atoms, really. I guess it's going to be the total number of pairs of electrons, really. So that might need to be modified a bit, because we're really more concerned about how many pairs of electrons are bound into the metal ions, and we'll get to how many that is in a bit, but that's called its coordination number. So the central metal and ligands bound to it then are what make up what's called the coordination sphere. And you'll see, we represent this in a very special way. So what is called the coordination sphere will be very obvious when you look at the formula of a complex. Different arrangements of ligands are possible, and those create isomers. An isomer is a structure or two or more structures that have the same kinds of atoms in them, but the atoms are arranged physically differently in space. So whenever we can physically arrange something in two or more ways using just the same atoms that we had before, those are called isomers, equal existence. So the isomers then are different arrangements which will give different physical and chemical properties. You can have the same formula, but two or more different physical arrangements. Those will have things like different colors, different melting points, different odors even. And so they are chemically and physically distinct. So studying isomers is a big deal in chemistry as well. The metal-ligand bond. This is the interaction between, of course, the metal, which acts as a Lewis acid, and has at least one empty d orbital in order to coordinate electrons, and a Lewis base, which is the ligand, a pair of electrons, at least one pair of unshared electrons, that is going to coordinate into those empty d orbitals. So a Lewis acid is an electron pair acceptor, a Lewis base is an electron pair donor. Complexes display physical and chemical properties different from those of just the metal by itself or the ligands by themselves. Once those ligands coordinate into the empty d orbitals of the metal ion, you have created a new compound with its own unique set of physical and chemical properties. The charge on a complex ion equals the sum of the charge of the metal plus the charges on the ligands. Usually, now, of course, the metal is going to have a positive charge, and the ligands, if they have a charge, will be negative. So in a complex, the donor atom is the atom bonded directly to the metal. The coordination number is the number of ligands attached to the metal, and like I said, that's going to really be more about the lone pairs rather than the atoms or molecules themselves. And the most common coordination numbers are 4 and 6. You might find other numbers, but almost everything, especially here at this freshman level, are going to be either 4 or 6. So if you have absolutely no idea, pick either 4 or 6. And even out of that, most of them are 6, because they want to occupy what's called an octahedral geometry, which you should have learned about in General Chem 1. Whenever you have 6 positions around a central atom, that is octahedral geometry. But some of them form 4 coordinations, but most are 6. And so any number other than 4 or 6 is fairly rare. And so, again, even if you have absolutely no idea, choose 6 just because you'll probably be safe at that. But hopefully you will have an idea, and you'll do this from an intellectually informed position here. So some metals have a constant coordination number, like chromium-3 and cobalt-3. Those have coordination numbers of 6. The size of the metal ion and the size of the ligands affects the coordination number. So like iron-3 can have coordination, or can coordinate 6 fluorides, but only 4 chlorides. Chloride is way bigger than fluoride, so even though chloride's right underneath fluoride on the periodic table, chloride is much larger than fluoride. So 6 fluorides will fit around the iron-3, but only 4 chlorides will. And so you can either have Fe, F6. Oh, by the way, these brackets, this is what defines the coordination sphere. Everything inside the brackets in this context is inside what's called the coordination sphere. Everything outside it is just bonded to the outside electrostatically with ionic bonds. But everything inside is coordinate covalently bonded. And so you can see the difference in the complex, that you could have 6 fluorides or 4 chlorides bonded to the iron. I do not expect you to be able to tell that, though. You're going to only be focusing on being given a formula or a name, and from the formula being able to tell what the oxidation number of the metal is and what the coordination number of the metal is. All right, so geometry. 4 coordinate complexes have 2 common geometries. They will either form tetrahedral or what's called square planar. The 4 atoms will bond around a flat plane, making just a 2-dimensional molecule then. But if it's tetrahedral, then it has 3-dimensional geometry, as you learned about a long time ago. 6 coordinate complexes are almost always octahedral. I cannot think of any that aren't, but it doesn't mean that there aren't. But so 6 coordinate systems are octahedral in general, and if it's 4 coordinate geometry, it'll either be tetrahedral or square planar. And again, you'd have to be looking at it 3-dimensionally to know, because I don't expect you to know just, oh, well, that's obviously going to be tetrahedral, or that's obviously square planar, just by looking at the formula. I would provide you the picture of it, and you could tell me whether it's tetrahedral or square planar then. Common ligands. Now, in Blackboard, I have a handout in there that goes over the nomenclature, and that also contains all of the common ligands as well. Now, ligands with their lone pairs are said to be taking a bite out of the metal. Yes, literally, they are referred to as taking a bite out of or into the metal. They're biting into the metal. And so the dentate teeth, one lone pair of electrons equals one tooth. So if there's only one bite being taken into the metal, it's called a monodentate. So if only one lone pair of electrons is being donated as a Lewis base to the metal, that is monodentate. If two lone pairs of electrons are being donated by the same molecule, that ligand is said to be bidentate. Some ligands have three or more lone pairs of electrons on the same molecule that are capable of being donated as a single Lewis base to the metal ion, and so we refer to those as polydentate, many-teeth ligands. These many-dentate ligands are also called chelating agents. The chelate, if you've had enough biology and you think about a lobster or a crawfish or something like that that has that big old pincer, that pincer is its chelator. And so the chelating agent then takes many bites into the metal. And so we pinch into it, if you will. But so dentate itself comes from tooth. One lone pair equals one tooth. Two lone pairs is bidentate, and many teeth then is polydentate, which then we just refer to as chelating agents because of the way the molecule has grabbed onto the metal. All right, so chelating agents grasp the metal between two or more donor atoms. And so I know that's in direct violation of what is said here. Chelating agents have three or more, but it really should say that chelating is two or more, and that's the way I'm going to treat it. So I apologize for the ambiguity in this outline, but chelating agents are going to take two or more bites out of it. So whether it be bidentate or polydentate, they're all chelating agents. The only one that's not is monodentate. So chelating agents grasp the metal between two or more donor atoms on the same molecule. So the molecule has two lone pairs of electrons on different parts of the molecule that are going to coordinately, covalently bond to the metal. So again, I apologize here. Polydentate, three or more, but chelating is two or more donor lone pairs of electrons. All right, and so chelating agents form more stable complexes than do monodentate ligands, and the chelate effect refers to the larger formation constants for polydentate ligands as compared to corresponding monodentate ligands. Chelating agents are sometimes referred to as sequestering agents. The reason for this, then, is that especially a certain chelating agent called ethylene diamine tetraacetic acid or ethylene diamine tetraacetate, that has a chelation of 6. It's polydentate, and it's going to donate 6 pairs of electrons. It's a really big molecule, and so it's going to take up all of the possible places on a metal atom, so that it forms an octahedral complex just by the one molecule, which then completely and totally surrounds the metal and therefore has sequestered it, has hidden it away. Sequestering is talking about hiding something away. And so if you sequester the metal, it is unavailable for any other kind of bonding. You've completely enclosed it in the chelate. So that is sequestering. And this is what is done with heavy metals like lead or mercury. If a small child has eaten lead, paint, or whatever, and you can get them to treatment fast enough, then they give them EDTA solutions, which will then bind the lead and mercury, irreversibly, and then it'll pass out of your system. If the lead or mercury gets into the system physiologically, like survives the stomach and then enters the actual bloodstream, mercury tends to go to the liver, and lead tends to go to the brain. And so in children whose brains are still developing, if the lead gets into the brain, it will not come back out. It is there permanently at that point, and it will cause damage to the developing brain and cause developmental problems. Mercury is toxic. It gets into the liver and keeps the liver from doing its job. But if someone has just taken a dose of either mercury or lead, and you can get them to treatment fast enough, the EDTA, while it's still in the stomach, will sequester those metals and allow them to pass out of the body without getting into trouble. They won't get to the liver, they won't get to the brain. They'll pass right out of the system straight through. All right, so important chelating agents then, ethylene diamine, which we will use in laboratory to synthesize a complex, ethylene diamine tetraacetate, which is the 4- version of the ethylene diamine tetraacetic acid. The acetate's much more soluble in water and therefore able to be used more effectively. Then there's also the oxalate ion, which is C2O4, 2-. Oxalate is one of the polyatomic ions you should have memorized a long time ago. And the abbreviations that we use in coordination chemistry for ethylene diamine is EN. So if you see an EN, especially in parentheses, that is referring to ethylene diamine. Or if you see OX, that's referring to oxalate. EDTA, of course, is obvious, referring to ethylene diamine tetraacetate. Okay, so the metals and chelates in living systems then include 10 of the 29 elements required for human life. For they're transition metals. 29 elements are required for you to live. 10 of them are transition metals: vanadium, chromium, manganese, iron, cobalt, copper, zinc, molybdenum, cadmium, and nickel. And so a lot of these are contained in enzymes. So you'll see like cobaltamine, one of the B vitamins, or a couple of the B vitamins. And so a lot of these are in the form of enzymes. You don't see them just floating around anywhere. And so then say many natural chelates coordinate to the porphine molecule. Again, if you've had enough biology anyway. So porphine forms a tetradentate ligand with the loss of 2 of the protons bound to its nitrogen atoms. And so a porphyrin is a metal complex derived from porphine. Now, again, you don't have to know structures and all, but it's important to understand that important porphyrins include heme, so where we've got the metal complex of iron 2 bound to porphine, you've got heme, which is then going to contain or bind oxygen to travel to and from tissue. So from the lungs to the tissue, heme binds oxygen reversibly by using iron 2 in the middle of that porphyrin complex. For chlorophyll, then magnesium is the metal that's bound into the porphyrin for whatever the plants do with their chlorophyll. All right. So again, metals and chelates are very important in living systems for what they do naturally, but we can also use them in just chemistry, usually inorganic chemistry, to make important compounds that can exert a medical effect and so on. Before we do the lecture problems, make sure, please, now we're going to talk about nomenclature in a minute, but in order to be good at this, go back here to section 2 where we talk about the dentations. In that handout in Blackboard, you really need to spend a little time, so pause the video if necessary. But study that handout in terms of memorizing which ligands are either monodentate, bidentate, or polydentate. Because in order to tell the coordination number of a complex, a formula that's given to you, you're going to have to know how many bytes it takes out of that metal. So again, pause if necessary, study which ones are mono, bi, and polydentate, because you got to know those just on site. And so once you've studied those, now let's go to my apologies, to the lecture problems and have a look at those. Number 1, for each of the following, there's 4 of them, for each of the following, tell both the oxidation number and the coordination number of the transition metal in each of the complex. Okay, so for the first one, K3, then a bracket, CO, parentheses, CN6, close bracket. Okay, so this compound, now remember, in the bracket is the coordination sphere. Yeah. So in the coordination sphere, that's the bracket. This out front is just associated to make overall charge 0. Because remember, the charge on all compounds is zeros. So those counter ions outside of the coordination sphere only exist as electrostatically bonded particles to make the overall charge 0. What we really care about is what's inside the coordination sphere. All right, so let's do the coordination number first. How many bytes does this have taken out of it, this cobalt that we're looking at? Because coordination number is easier than oxidation state. That's going to take a little bit of work. All right, but you look at this, the ligand here is cyanide. But when it's bonded in the coordination sphere, its name changes to cyano. Cyano is a monodentate ligand, and there are 6 of them. Therefore, if it's monodentate and there are 6 of them, that's 6 bytes into the metal. Therefore, its coordination number is 6. Really straightforward, right? All right, but now for oxidation number. What we have here is we have 3K plus, so that gives us 3 pluses overall, right? Cn is not negative, so that's 6 negatives overall, correct? Okay, hopefully you're with me so far. The potassiums are always 1 plus, and there's 3 of them, so there's overall 3 positives. Cyanide is always 1 minus, and there's 6 of those. The difference in these charges is going to be the charge on the cobalt. And remember, it should always be plus. Cobalt, the metals themselves have to have a positive charge or 0, because it could be an oxidation number of 0. So the oxidation number, now again, is going to be the result, the difference, between any electrostatic ions, whether they're cations, or if this overall was positive, there would be anions to make it all 0, and we'll see that. All right, but the 3 potassiums and the 6 cyanos end up being overall 3 negative. This means that the cobalt must be 3 plus to make overall equal to 0. So, I apologize. The oxidation number is not the same as charge. Oxidation numbers, unlike charge, remember with the charge, you have to have number first, sign last. With oxidation number, like formal charges, you must do sign first, number last. It will be wrong if you don't put it that way. Sign first, number last for oxidation number. So for this complex, the coordination number is 6, and the oxidation number is plus 3. And again, you have to write it that way. Let's do another one. For the next one, we have platinum, En2, close bracket, and then we have ClO4, 2. Okay, so again, if we look at coordination number, En, ethylene, diamine, and that is bidentate, because you remember this, you've studied it now, right? And you remember that ethylene diamine is bidentate, and there are 2 of them, so that's going to give 4. That has a coordination number of 4, because there's 2 of them, and each one is bidentate, so that gives me a total of 4 bytes into that platinum metal. So now oxidation number. All right. So we have the perchlorates. Now the perchlorate is 1 minus what you should have remembered a long time ago. So that's going to equal 2 negatives, right? En is 0 charge. It's a molecule and has no charge associated with it. So the difference then is 2 minus. So the PT must be 2 plus to make it 0. So the oxidation state is plus 2. Remember, for charges, you have the number and then the sign, but for oxidation, you must have sign then number. All right, so for B, coordination number of 4, oxidation number of plus 2. Third one. Fe, NH3, 4Cl2, close bracket, Cl. All right. All right, coordination number. So again, we're talking about in here. So NH3 equals monodentate, Cl equals mono. And there's 4 of the amines and there's 2 of the chloros. So that's a total of 6. The coordination number on there is 6. Each amine is taking 1 bite and each chloro is taking 1 bite. All right, so now oxidation number. All right, so the chloride on the outside, and honestly, we can do it all the way around, but the chloros then is minus, and there are 3 of them, so that's going to be a total of 3 minuses. NH3 is 0. Therefore, we have an overall 3 minuses, both inside and out in this case. And so then Fe must be 3 plus then to counteract that, because all charges have to add up to 0. So the oxidation state then is plus 3 for that. Coordination number 6, oxidation number plus 3. One more. Chromium, Ox2. Yes, and water can be a ligand just as well, and it's quite common that it is. And NO3 too. All right. Coordination number. So again, we're only looking inside. Ox is bi, and there's 2 of those. H2O is mono, and there's 2 of those. So add this up, and that gives you 6. Coordination number is 6, because each ox is going to take 2 bites, and each water is going to take 1 bite. And so that's a total of 6 bites. Oxidation number then. NO3 is a 1 minus, and there's 2 of those. So that's 2 minus. H2O is 0. Ox is a 2 minus, and there's 2 of those. And therefore then, that's going to be a total of 4 minus. Okay. So, when we look at this then, that gives me a total of 6 minuses. Wow. That CR must be 6 plus then. So oxidation number of plus 6. And that's important because, chromium 2 and chromium 3 are common and around, and chromium 3 is even used in some supplements to, supposedly give you energy and all that nonsense. But chromium 6, chromium 6 is mutagenic. And so if you're ever in a position where you know that you're dealing with a chromium that is in a +6 oxidation state, so we call it chromium 6, that is mutagenic. You handle it with gloves, maybe even wear a mask, and treat it with great care that you don't get it on you or around you, and make sure you thoroughly wash and all that good stuff. Because with mutagenic substances, it doesn't take much to cause you damage, and even like one exposure, some years later, can come back to haunt you in the form of cancer. So do handle those with caution. All right. So irrelevant to answering the question, but it's just ancillary information you should know. Coordination number of 6, oxidation number of +6. All right, so that's it for that question. And we go back to the outline and talk about nomenclature really quickly. Complexes are named in a systematic manner using some simple nomenclature rules. And so there's a handout out there for you still on this, but here in the outline, for salts, the name of the cation is given before the name of the anion. Within the complex ion or molecule, the ligands are named in alphabetical order before the metal. The names of anionic ligands end in O, such as oxalato or cyano or chloro. And for neutral ligands, the name of the molecule is used. Although, ammonia becomes amine, so that's a little bit of a change, and water becomes aquo, and so on. But so some of this isn't as straightforward as it should be. But anionic ligands end in O, and neutral ligands is a little more complicated because you have to know in context. Like ammonia is no longer ammonia, it's amine, and water is no longer water, it's aquo. But you have to memorize those. That's in that handout. Greek prefixes are used to indicate the number of ligands, di, tri, tetra, penta, hexa, so on, if there are. But if the ligand already has a Greek prefix, like ethylene diamine, then you have to enclose the name of the ligand in parentheses and use bis, tris, tetrakis, pentakis, or hexakis. We'll only be on bis and tris, by the way. These others, that gets more complicated. But so bis and tris might be a fair game for this. And if the complex is an anion, the name ends in 8. So even though it's a metal that's in the complex, it will gain an 8 because the overall complex coordination sphere is negative. So we put an 8 on the end of the name. The oxidation state of the metal is then given in Roman numerals like we're used to, in parentheses after the name of the metal. And so let's do the nomenclature then. Let's go back to our drawing pad and let's do these nomenclatures real quick. All right, so what is the correct name? So the formula is CdEnCl2. And now notice there's no cation or anion. This is a neutral complex then. All right, and so there's no need to name a cation or anion since, like I said, it's a neutral complex. So to name this then, we look at what's in there. So the En is ethylene diamine, and the Cl is chloro. So we have to do them in alphabetical order, but notice there's also 2, so it gets di put on the front of it. All right, so alphabetical order. And by the way, alphabetical to the name of the ligand with a prefix put on the front, that does not change its alphabetical order because that's a prefix. Regardless of how many there are, the ligands are still named in alphabetical order. All right, so then we do the metal last, ligands first. So this becomes dichloro, and then there's only one of these, so there's no need for any other prefix. So we just then say dichloro ethylene diamine, and then the name of the metal, because that we've already named these ligands. So now that metal is cadmium, and we need its oxidation state. So you have to work that through too. The chloro, or the En, then let's say is neutral, and the Cl is 1 minus, and there's 2 of those. So that makes 2 minuses, which means the cadmium then must be 2 plus. And so then we put Roman numeral 2 in parentheses there. And then there's no anion to put out there, so this is the name. Dichloroethylene diamine cadmium 2 is the way you would say that. All right, let's do another. We are given Cr, NH3 4, CO3, close, and Cl. All right, so if we're going to name this thing, and first just real quick, because we know we're going to need the oxidation number, so let's quickly do that. CO3 is 2 minus, NH3 is 0, and there's only one of those carbonates, carbonatos, and so then that's, oops, why did I do that? So that equals 2 minuses, and then the Cl is a minus, so there is a total of 3 minuses, so Cr must be 3 plus. All right, so we have that out of the way, so that's going to be plus 3, or for the name, 3 in Roman numerals. All right, so get this out of the way because we need the space here. Make that more effective. Okay, so now for the name, we've got NH3, which is amine with 2 A's, and there are 4 of them, so that's going to be tetra. And then we have the CO3 2 minus, which is carbon auto. All right, so if we put this together, then, of course, by the way, the Cl is chloride. All right, so inside of the coordination sphere, amine comes before carbon auto. It had nothing to do necessarily with how these were placed. Because how these are placed inside the coordination sphere is more advanced, which way you would put them. But right now it's irrelevant. We're still just going to figure out what the names are and put them in alphabetical order. All right, so inside the coordination sphere, then A becomes before C. And so again, regardless of the prefix, so this is tetraamine, right? Carbon auto, right? And element is chromium. Its oxidation state we found is 3. And then we need the anion name. That's a separate word, and that then is chloride. Oops. Let's do that better. Now, as far as this goes, the rules you learned a long time ago about ionic compound nomenclature still apply. If there were 2, 3, 4, or 5, whatever of these chloros out here on the outside, it's still just chloride because it can only go together one way. So you do not put a prefix on those outside of the sphere, regardless of whether it was a cation in front, however many there were, or an anion at the end of the formula. However many there are is irrelevant. You only just use the name of it. Do not put a prefix on there. Okay, so now you've named 2 of these. Can we go the other way? Oops. There we go. Tetra, aqua, dibromo, manganese 3 chlorate. Yeah. So, by the way, if you have neglected keeping up with your polyatomic ions and all from the beginning of Chem 1, you got to go dig those out and learn them again because it's all fair game. All of that stuff from back then is still fair game here. All right, and so let's take this apart. Aqua is H2O. Tetra is 4. So that's going to be H2O sub 4 as this piece then. Oops, this piece. Dibromo, then Br, and there's 2 of them, so that's going to be Br sub 2. Mn. All right, and so this is all the coordination sphere then. So if I'm going to put a formula for this, I'm going to open it up. Metal goes first, and honestly don't care whether you put the H2O or the Br first. I'm going to put the H2O first. Sub 4, Br2. Now close this because that's all that's in this coordination sphere. And it must have a positive charge because it has an associated anion. And you will remember that chlorate is ClO3 1-. Now, so to determine how many of those we do need to do a little bit of work here and figure out what the charge is inside. Because it is manganese 3. So we know that's a +3 here, right? And the Br is a -1, and there's 2 of those. So that's +3, and that's -2, which is going to give an overall +1. And chlorate's already -1, so there is only one of the chlorates then, because we need the charges to always add up to 0. And since the charge in here, this whole thing, thought I changed it. There we go. This whole thing here as a +1, so outside needs to be a balance of -1, so there is only one of those. So the correct formula then for this first one is this. Okay, let's do another one. Clear this all out. And go back here. So now it is cesium, diamine, tetracyano, chromate 3. Notice the chromium actually has an ATE ending on it because it must be in the anionic form then. So that overall complex itself is going to have a negative charge because instead of chromium, which would mean it's in a cationic version, this chromate, which means the complex, not the metal itself, but the complex is overall negatively charged. All right, so again, let's start tearing this apart. Outside of the sphere, the cesium, Cs, cesium is an alkali metal, and therefore it's going to have a 1+ charge. So we'll have to figure out how many of those we'll need in a minute. Inside of here, then inside of the sphere, we have 2 NH3s, we have 4 cyanos, which are 1-, and then you have the Cr, which is 3+. All right, so let's find out overall charge here then. This is 0, this is 4 minuses, and this is 3 pluses. Therefore, we end up with 1- overall, so we're only going to need one of those cesiums then. All right, so let's see about putting this all together. Cation goes first, so Cs, then open the bracket for the complex. Chromium is your first entry because that's the metal. Then you have, and again, we'll just put them in order. Diamine, so that's NH3, parentheses 2, and then tetracyano, which is parentheses CN4. Now remember, if they're just one thing, if they're monoionic, then monoatomic ions, then they only have the subscript after them. But if they are polyatomic and there's more than one, you have to enclose them in parentheses, by the way. So that's why NH3 being polyatomic has to be in parentheses sub 2. CN is polyatomic, so parentheses sub 4. Then we can close that. And there's no anion because we had a cation. So the correct formula for cesium diamine tetracyanochromate 3 is going to be this formula here. And so there, of course, is practice out there for you to do. There are supplementals in Blackboard for this topic, both to go from name to formula and formula to name. You'll have both of those to practice with. Finishing out this chapter, though, then we come down here. And so if we have two compounds with the same formula but different arrangements, they're called isomers, as we said earlier. Structural isomers have a physical different arrangement of the bonds, but stereoisomers have the same bonds but different spatial, three-dimensional representation. So the same bonds in the same locations, but spatially they're locked into a different arrangement, which still gives you different physical and chemical properties. When we get to organic chemistry, this idea of structural isomers versus stereoisomers becomes really important. Here for metal ions, we're just defining the terms. So definitions are still fair game for an exam, but I want you to understand right now we're just introducing the terms. When we get to organic, you will see a lot more about how to write and understand and differentiate between structural isomers and stereoisomers. All right. The last section then, color and magnetism in coordination chemistry. One of the coolest things about coordination chemistry are the colors. And when we do a lab experiment involving the synthesis of a coordination compound, you're going to see how the colors change from the metal the way it is originally versus whenever you put a different ligand into it, how it changes color. Because a lot of the colors are really beautiful colors on the transition metal complexes. So coordination chemistry is just fun from a synthetic point of view, one, just because you get to see the colors. And then we'll come back to magnetism, which we talked about in 105 also in the General Chem 1. But for color then, color of a complex depends on the metal, the ligands present, and the oxidation state of the metal. A partially filled d orbital is usually required for complex to be colored. If the orbitals are completely empty or completely full, then those tend to be colorless complexes, or white crystalline solids. But if you have especially unpaired electrons in d orbitals, that's going to give you some really nice colors. So it depends on how the ligands bond into the d orbitals, which is much more advanced than we can do here. If you're going to stay in chemistry, third year, you will take an entire course in inorganic chemistry, and you will see how the d orbitals actually split apart, and it makes a difference on where the ligands coordinate in which part of the d orbitals, in order to make those different colors, those electronic transitions into the visible range. Magnetism, we talked about diamagnetism and paramagnetism in General Chem 1. And so many of the transition metal complexes are paramagnetic. That means they have at least one unpaired d electron in their system. And so that means they're drawn into a magnetic field. So we do a test, what's called magnetic susceptibility. You put a little bit of the compound onto a pan, and then you put that pan in toward a magnetic field. If the pan is drawn in because the compound is drawing it in, it's paramagnetic. If you try to put the pan in the magnetic field and the pan is being pushed back out, then it's diamagnetic, which means all the electrons are paired. So compounds of cobalt, such as the hexamine cobalt or the hexafluorocobalt. So the hexaamine cobalt has no unpaired electrons, so it's diamagnetic. But if you use 6 fluorides, so the hexafluorocobalt has 4 unpaired electrons in it, so it is paramagnetic. when you get to third year, I'm only introducing this term, you are not responsible for this, but once you get to third year inorganic chemistry, then crystal field theory is something that you'll go into a little deeper, and that describes bonding in the transition metal complexes and tries to account for both the color and magnetic property, because the d orbitals are way more complicated than they've been shown to you in both semesters of general chemistry. So by the time you hit third year, you'll have enough sophistication to understand how the d orbitals really are and how they're split apart. But don't worry about that crystal field theory here. I'm just introducing the term. This concludes the lecture on Chapter 17.